T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
MDS to
We have ignition. We have a liftoff.
roll program is in on time. Vehicle response is normal.
In 1977, two pioneers embarked on what might be one of the most epic feats of exploration ever undertaken. Their goal? To unravel the cosmic mysteries surrounding the solar system and our place in it. Not only did they provide us with some of the first and best imagery of our solar system's outer planets, but they continued to send us incredible new information about our universe from interstellar space, some 47 years and 24 billion kilometers later. The Voyager 1 and 2 probes are more than just instruments and circuitry. They are a symbol of humanity at its best. Curious, audacious, ambitious, and resilient. Voyager didn't just capture dazzling photos of our gas giants and their moons. It captured the hearts and minds of generations back home on Earth. These are the probes that have gone the furthest that any human object has traveled. They are trailblazers and groundbreakers. It is their unique opportunity and their peril to travel beyond the reach of humanity, to capture images of things we have never seen before so close up, nor have we seen since. When I look back, I realize how little we actually knew about the solar system before Voyager, says Voyager mission project scientist Edward Stone. We discovered things we didn't know were there to be discovered, time after time.
Its trajectory was designed to take it past Jupiter in March 1979 and Saturn in November 1980. Interestingly, when it approached Jupiter, the spacecraft's cameras captured intricate cloud patterns, massive storms, and the planet's faint ring system. One of the mission's most iconic images is the detailed view of the Great Red Spot, which is a gigantic storm larger than Earth. Voyager 1 also turned its attention to Jupiter's moons. It discovered that Io is the most volcanically active body in the solar system, showing erupting volcanoes and vast lava flows. In addition, its images of Europa revealed a smooth, icy surface, hinting at the possibility of a subsurface ocean beneath the moon's icy crust. A year later, the Voyager 1 reached Saturn. The spacecraft's images showcase the intricate structure of Saturn's rings, revealing countless ringlets and gaps within the rings, including the previously unseen F ring. Like with Jupiter's moons, Voyager 1 provided detailed views of Saturn's moons, but perhaps the most significant discovery was the thick, orange atmosphere of Titan, Saturn's largest moon. The dense atmosphere, rich in nitrogen and hydrocarbons, suggested the presence of complex organic molecules.
It's one of life's little ironies that it is not new, cutting-edge technology that is advancing our understanding most at the edge of our solar system, but old machines. They have an onboard computer with less memory than the one inside your car's key fob. To this day, they are still using 8-track magnetic tape from the 1970s, which makes them older than many of you sitting here watching this. This is the conundrum of deep space exploration, where vast distances and extremely long travel times can mean that technology is antiquated by the time it has reached the most ambitious targets. Of course, Voyager 1 and 2 were not initially meant to travel all the way to interstellar space. They were instead built for a 5-year mission to explore Jupiter and Saturn and their larger moons, which was only possible thanks to a rare, once every 176 years planetary alignment. However, after completing all of its initial objectives on Jupiter and Saturn, the Voyager mission team added flybys of Uranus and Neptune to one of the probe's objectives. Later, these too were completed, so NASA announced the start of the even more ambitious Voyager interstellar mission, with the purpose of exploring the outer limits of the Sun's sphere of influence and beyond. This final journey would take both probes off the ecliptic to unexplored parts of the solar system, such as the termination shock and the denser and hotter heliosheath, before finally crossing the heliopause into interstellar space.
These large dishes are capable of communicating with spacecrafts billions of miles away, which is how they can communicate with the Voyager space probes. The signals travel at the speed of light and can take around 20 hours to reach Earth. This is because the Voyager 1 uses the high-gain antennas to direct a narrow beam of radio waves towards Earth, and since radio waves are a form of electromagnetic radiation, they travel at the speed of light. The spacecraft's ability to communicate and operate is fueled by radioisotope thermoelectric generators. These generators harness electricity from the heat released by the decay of plutonium-238, powering Voyager 1's instruments, onboard computers, and radio transmitters. The RTGs, with a half-life of about 87.7 years, experience a power decline of roughly 4 watts annually. It is anticipated that by 2025, Voyager 1 will lack sufficient power for any scientific instrument operation. Beyond this point, although Voyager 1 will continue its silent journey through space, we will no longer receive new data or signals from the spacecraft. But in any case, the Voyager 1 carries a golden record, which is a 12-inch gold-plated copper disc containing sounds and images selected to portray the diversity of life and culture on Earth. It's a time capsule intended for any extraterrestrial life form or future humans who might find it. The record includes greetings in 55 languages, music from various cultures and eras, natural sounds of Earth, and a selection of images showing life and the human condition. So how far can the Voyager 1 even travel? Realistically, based on its trajectory and the vastness of space, the Voyager 1 is far more likely to experience structural degradation over time due to factors such as micrometeoroid impacts, cosmic radiation, and thermal cycling than to be significantly affected by the gravitational influence of a star or planet. Therefore, it's possible that Voyager 1's structure could remain recognizable for hundreds of millions to a few billion years, barring any catastrophic collisions with large objects.
While a radioisotope generator meant that power production was in constant decline, it would halve in strength every 87.7 years, it would still be enough power to keep the essentials on the probes running until at least 2025. This long-term fuel capacity was no accident. You see, when the Voyagers launched in 1977, NASA faced a unique opportunity. The planets would soon be in that 1 in 176 year alignment that had last occurred during Napoleon's first reign. This rare alignment would not only allow the Voyagers to visit Neptune and Uranus with minimal course adjustment, but also give the probes a gravity assist from each of the 4 outer giants they visited, thereby increasing their effective velocity beyond what they could get from their own rocket propulsion. This idea was relatively new at the time, having been only attempted previously on NASA's Pioneer missions to Jupiter and Saturn. However, this narrow window gave NASA a strict deadline. There wasn't enough time to plan follow-up missions, and the United States Congress wouldn't earmark enough funding for a longer expedition, like the Grand Tour NASA first proposed. So, what did Voyager's team do? They devised a series of engineering feats to optimize the probes for a potentially longer mission and fervently hoped that the funding would follow.
By this time, it will have traveled around a quintillion miles, which is only about 1.7% of the Milky Way's diameter, but it would have seen numerous stars. Given its current trajectory towards the constellation Ophiuchus, during its lifetime, the Voyager 1 could potentially pass by the constellations Hercules, Lyra, Cygnus, Draco, and Camelopardalis. The number of stars in these constellations could range from 1,000 to tens of thousands. It's worth noting that over billions of years, the spacecraft's trajectory will be influenced by many factors, including gravitational encounters such as those from molecular clouds, passing stars, or even the tidal forces from the Milky Way itself. As the Milky Way rotates, its gravitational forces and those of nearby galaxies and interstellar objects will subtly alter Voyager 1's course. These changes, though small over short timescales, can accumulate to significant deviations over eons. Furthermore, over such vast timescales, the stars themselves will have moved significantly from their current positions, and the constellations as we know them will have altered or ceased to exist in their present forms based on new stars forming and old ones dying, ensuring that the galaxy of the distant future will be significantly different from the one we see today.
Voyager 1, launched in 1977, is the most distant spacecraft ever sent from Earth. It is moving away from us at a speed of about 38,000 miles per hour, or roughly 11 miles per second. Despite its staggering distance of about 15.5 billion miles from Earth, we are still able to communicate with it. So, how is it possible to send commands to such a distant spacecraft or receive data from it? And how much longer will we be able to stay in contact with Voyager 1? Voyager 2 was actually launched first, on August 20th, 1977. Voyager 1 followed about 2 weeks later, lifting off on September 5th, 1977. Voyager 1 and Voyager 2 are nearly identical in design. Their mission was to explore the outer planets beyond Jupiter. Rocket engines alone could not provide the necessary speed, so mission planners chose a rare planetary alignment that allowed the spacecraft to gain speed by using the gravitational pull of multiple planets. Jupiter, Saturn, Uranus, and Neptune were lined up in the same general direction as seen from Earth. This alignment will not occur again until the year 2150. Voyager 1 flew past Jupiter and Saturn, sending back breathtaking images along the way. This image shows the atmosphere of Jupiter. It also confirmed the presence of Jupiter's faint rings. Voyager discovered active volcanoes on Jupiter's moon Io. It then headed toward Saturn. There, it observed Saturn's rings from a close distance and discovered shepherd moons that help shape and maintain the rings. It also found that Saturn's moon Titan has a thick atmosphere composed of about 90% nitrogen. After that, Voyager 1 continued its journey toward the outer edge of the solar system. Voyager 2, which took a different path, flew by Uranus and Neptune, destinations that Voyager 1 never reached, and took detailed photos of both planets.
On the 20th of August 1977, NASA launched the Voyager 2 space probe from Cape Canaveral, Florida. Its partner in crime, Voyager 1, was launched 2 weeks later on the 5th of September. Even though both probes were Jupiter-bound, Voyager 1 was set on a shorter, faster trajectory, so taking off second made sense. It overtook Voyager 2 on the 15th of December 1977 and exited the asteroid belt first. Together, this dynamic duo was set to take a dazzling parade of pictures that were absolutely revolutionary at the time. But don't take my word for it. Let's jump in and you'll see for yourself. 13 days after launch, Voyager 1 sent this photo back to Earth. The first of tens of thousands it would send back over the next 5 years. Taken 11.6 million kilometers from Earth, it's a sentimental place to start our journey. It might remind you of the Earthrise photo taken by the Apollo 11 crew from the moon just 8 years prior. We can see our blue marble and its moon in the distance. I don't know about you, but I find this photo so hauntingly beautiful, especially knowing how far this probe had travelled and how much it's seen since then. But we've got a long way to go, so let's move on. It would be almost 2 years before Voyager 1 finally makes its approach to its first target, Jupiter. Not bad, considering it's 714 million kilometers away. Voyager 1 arrived first on the 5th of March 1979. You see, it travels at 17 kilometers per second, 2 kilometers per second faster than Voyager 2, who, despite leaving Earth first, arrived 4 months later on the 9th of July 1979. This is because the trajectory Voyager 1 took allowed it to gain more speed relative to the Sun. Now, Voyager 1 was not the first spacecraft to encounter Jupiter. That was Pioneer 10, 7 years prior in 1972. And while the Pioneer mission certainly provided great scientific insights, it didn't quite grab the imagination of the public. But sending back stunning images like this, Voyager certainly did. This is Jupiter in all its glory. It's kind of hard to accept that these are actual photos and not paintings or some AI-generated image. If you look closely, you can spot two of its moons, Io on the left and Europa, the beige one, on the right, but more on them later. Luckily for us, Voyager 1 even recorded its approach to the great gas giant. It took photos at regular intervals, every 10 hours or 1 Jupiter day. This means the planet is in the same point of its rotation in all the photos. The 66 photos were spliced together to create this time-lapse movie, spanning Voyager 1's approach to Jupiter from the 6th of January to the 3rd of February 1979, covering a distance of 27 million kilometers. I personally can't decide if it is incredible or terrifying, but let's get a closer look and see what surprises this planet is hiding. Something that immediately stunned scientists was Jupiter's atmosphere. They expected to see east-west and west-east winds in Jupiter's different atmospheric zones, but what caught them by surprise was the amount of turbulence, plumes, and rotational movement, which are super clear in this image. You can immediately see how dynamic the atmosphere of Jupiter is.
Particles coming from interstellar space. So, the heliosphere marks the limit of the Sun's influence via the solar wind. The solar system itself is much larger. For example, the Oort cloud lies far beyond the heliosphere. The Oort cloud is a theoretical region filled with icy bodies and rocks surrounding the Sun in a vast spherical shell. According to some estimates, it will take Voyager another 300 years to enter the Oort cloud, and about 30,000 years to exit it. We can still send commands to the Voyagers and receive scientific data from them. But how is communication possible over such vast distances? Each Voyager has a dish antenna that is 12 feet across. This is the iconic feature most people imagine when they think of the spacecraft. The antenna emits a very narrow beam of radio waves with just 22 watts of power, the equivalent of a household light bulb. It takes about 22.5 hours for a signal to reach Earth. For comparison, it takes just over 1 second for light to travel from the Earth to the Moon, and about 20 minutes to reach Mars. This puts the Voyager's distance into perspective. Radio waves weaken with distance, following the inverse square law. So by the time Voyager's 22-watt signal reaches Earth, it has faded to just a tiny fraction, less than 1/trillionth of a watt, and then another billionth of that. To detect such faint signals, NASA uses massive antennas. These antennas are 230 feet in diameter and are part of the Deep Space Network. The network is set up at 3 locations: California in the United States, Madrid in Spain, and Canberra in Australia. This ensures that at least one antenna can always see the spacecraft at any given time, enabling 24-hour communication.